Good day, grade 12 learners. Welcome to today's geography lesson. My name is Cynthia Zondi and my co-presenter is Hendrina van Heerden. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Okay, grade 12 learners, today we are going to look at the lesson on subtropical anticyclones and associated weather conditions. Our lesson objectives are as follows, and this, remember, it is based on the revision work that you were taught this week. So this topic that you dealt with this week from the 5th to the 9th of February 2024. So here's what we are going to look at: subtropical anticyclones and its associated weather conditions. First, we're going to look at the location and identification of the 3 high pressure cells that affect South Africa. What are these 3 high pressure cells? We are looking at the South Atlantic high pressure cell, the South Indian high pressure cell, and the Kalahari high pressure cell. Okay, we are going to look at the characteristic of these 3 high pressure cells, and we also are going to look at how these anticyclones or these high pressure cells influence South Africa's weather and climate. And whilst we're doing this, we are going to look at the integration of the high pressure cells with the plateau, the inversion layer, ocean currents, and ridging of South Atlantic high pressure cell between the summer and winter position. We are also going to look at reading and interpretation of information related to the 3 high pressure cells on a synoptic weather map, anticyclonic air circulation and its influence on weather and climate. Right, we are also going to include a lesson on the map work that you also were taught in this week of the 5th to the 9th. Right, in the map work, we are going to look at the magnetic declination and magnetic bearing. We are also what is it? Where is it? So these are your key questions. What is it? Where is it located? So we want to know that each of these geographic aspects that we are going to look at, where is it located? And we also look into why is it located there. So meaning we have to give reasons onto why its location is there. And then we also are going to look at what does it look like. So it means you'll be answering questions like when you are now describing. And then what impact are these aspects having onto our weather, as we are going to look at the impact of the South Atlantic high pressure cells into our weather. And then we're also going to look at how it can be managed. So the impact thereof, how can we manage the impact of these geographical aspects that we are going to be looking at, and how do you feel about it? So those are the key questions that even in the exams the geographers takes into account. So you have to take note of this, and in preparation of any exam or any test, you must be able to answer these type of questions. So now we're going to look at these subtropical anticyclones. So the name itself, anticyclone. So it suggests that these are high pressures. So you need to take note of that. And then also you also need to take note of subtropical. So the name itself suggests where we find these anticyclones within the subtropical regions or latitudes. Right, we are looking at an anticyclone. I've indicated that it is a high pressure And then we also looking at the fact that its name also suggests where it is located. So how then do we have this development of the high pressure? So the high pressure would develop due to convergence of air. As the air converges, then this air would be forced to sink onto the ground or onto the lower parts of the atmosphere. And then as it sinks, as you can see from the annotations that you can see here of the arrows here, it shows that air converges and it sinks. And then when it reaches the lower parts of the atmosphere, what are we going to experience? Then it diverges. So it sinks onto the ground or onto the lower parts of the atmosphere. And then as it lowers itself, then it diverges. So we can see now the divergence that we can identify there. So these are the characteristics of anticyclones, that they are formed due to convergence of air. Then when the air sinks, as it reaches the lower parts of the atmosphere, there is surface divergence. So that then results in the development of a high pressure. So the movement around the high pressure, then it would be the anti-clockwise movement, which is associated with the high pressure cells. What characteristic is this sinking air? The sinking air is dry. Remember, it is from the higher altitudes in the atmosphere. So due to loss of heat, then it cools down, and then as it sinks, then it comes down as dry air, which then results in the development of the high pressure. So key things to take note, it's upper air convergence. Due to upper air convergence, then we have air that sinks. So this would be your next explanation on how these anticyclones are formed. And then what characteristic of the air is it? The air that is sinking, it is dry. So it is because it's from the higher altitudes of the atmosphere, and then it has lost moisture. So now it is dry. So as it sinks, it would reach the lower levels of the atmosphere, and the movement of air there would be surface air divergence, which results in the development of these high pressure cells. And then the other thing that you need to note is that within the southern hemisphere, the movement of air around the high pressure cells, it is anti-clockwise. So the air moves in an anti-clockwise direction around a high pressure cell. Okay, so there's a diagram there that is showing this what I was indicating of the air that is sinking, the sinking air here. There we can see the air that is sinking, and even the use of color there, it shows that the air that sinks there, it's cold and dry, or it's cooler and it is dry. But due to pressure, as it sinks, it gains heat, which is due to adiabatic heating. So as the air sinks onto the lower surfaces of the atmosphere, it heats up at a adiabatic lapse rate. So the air that gets to the surface gets heated, and then we can then identify the surface air movement, which is going to be this divergence that we can see here. So all these gives us the characteristics of the air around the subtropical anticyclones. Right, we then look at how then do these high pressure cells develop. What you see here is the tricellular circulation, which you have learned about in grade 11. So let's look at the development of the high pressure cells. The high pressure cells develop where? Within the 30-degree latitudes. That is the position of the high pressure cells. That's where they are developed. Right, and then when you look at this diagram also, it is showing you this tricellular circulation. But before I can even explain how this high pressure developed here, let's look at other things that we are also given indication of. I have indicated that it is formed where? Within the subtropical high pressure belt, which is 30-degree latitudes there. And then also, when you look at where I am indicating this 30-degree latitude, look at the latitudinal position of South Africa. So South Africa is where it is found within this 30-degree latitude. So South Africa is in the subtropical high pressure belt. Looking at the map that you can see here, when we look at this map, we can see the position of South Africa. It is exactly within the subtropical high pressure belt. So meaning that our weather, it is largely influenced by these anticyclones that we are going to identify within the 30-degree latitudes there. All right. And then the other thing that you also need to take note is that, therefore, when South Africa is formed within the found within the subtropical high pressure belt, the South African climate is then dominated by what? By the sinking air. So what dominates our climate? It is because of the air that is sinking around it. So going into this diagram, which shows the tricellular circulation that I have indicated of. So within this latitude, the 0-degree latitudes, the equatorial latitude there, we have surface air convergence. So these arrows here are showing you the air that converges from the northern hemisphere and from the southern hemisphere. So the convergence of air results in the rising of air. These arrows are showing you the air that rises within the 0-degree latitude. Cooling takes place at the highest level of the atmosphere. When it cools, this air is forced to diverge. So we can then see that the arrows are now pointing in different directions. So we can see the divergence that is shown in that direction and in this direction. So the upper air divergence. Then the cold air that is diverged or that diverges then sinks onto which latitude? It sinks onto this 30-degree latitude. So we can see that the air that was diverted onto this latitude and the air that was diverting from the Ferrel cell. Remember, the cell that we have here would be the Hadley cell that is formed there. We have the Hadley cell that is formed there. And then the surface divergence of the air within the 30-degree latitude would result in the air moving in the opposite direction towards 60-degree latitude, and the warm air that would move towards the tropics there from the 30-degree latitude there. So the divergence of air within the 30-degree latitude is the one that is responsible for the formation of this pressure belt that influences our weather here. So the two cells that are responsible for the development of this high pressure belt, it is the Hadley as well as the Ferrel cell. These are the two cells that are responsible for the development of this high pressure belt, because what we see is from the Ferrel cell, due to upper air divergence, the air that diverges here would diverge back onto the 30-degree latitudes, and we would have the convergence that we can see here, and the air that is sinking, where now it sinks onto the 30-degree latitude. So what you saw on that other diagram, we can identify the convergence that we can see happening up here, and then the blue arrows here are showing you that sinking of cold air the cold, dry air. And as it sinks, it then results in what? The development of the high pressure. And what we can also identify there, it's the surface divergence, which now the warm air, the warm and dry air that we can find within the 30-degree latitude would be directed towards the equator, and then it would also divert towards the 60-degree latitude. So basically, these are the two cells that are responsible for the development of this subtropical high pressures. Okay, then we are also going to look at the location and identification of the 3 high pressure cells that affect South Africa. Remember, it is very important that we take note of how these 3 high pressure cells would have an influence over South Africa, because we've already indicated that South Africa is found within this subtropical high pressure belt. And even from the diagram, you could see that that is exactly the location of South Africa within the 30-degree latitude. Right, first we have the outline of the South African map, and we are now going to look at the location of the 3 high pressure cells. In the interior of the country, what do we find? We find the Kalahari high pressure cell. On the east coast of South Africa, we find the South Indian high pressure cell. And also, what would guide you would be the ocean over which we can identify the location of this high pressure cell. So it is over the Indian Ocean. And then on the west coast of South Africa, we have the South Atlantic high pressure cell, which is located over there, the Atlantic Ocean thereof. So these are the names that even you should get used to using whenever you are answering any of the exam questions. Your Kalahari high pressure. I know with different textbooks it may come out in a different name, like a continental high pressure. But for now, the reference that we're giving is to the Kalahari high pressure cell. So these are the 3 high pressure cells. They are located where? They are located along that 30-degree latitude that we identified them. All right. So let's look at how then they are formed and what characterizes them. All right. So we're looking at the South Atlantic high pressure cell first, and then the 2 arrows here. The blue, even the use of color, boys and girls, you need to know and understand that it would even give you some idea of the ocean currents in which we are talking about here. So these are cool or cold ocean currents, the use of the blue color there. And then which ocean currents am I referring to? Onto this side, we're having the red, which indicates that these ocean currents are warmer. So what are they? They are warm Mozambique currents. And how do these influence the development of the 2 high pressure cells alongside the east and the west coast? So on the west, we can identify the cold currents there, which are the cold Benguela currents. And then in the interior, we have the Kalahari high pressure. So this Kalahari high pressure, it produces clear skies, dry conditions over the interior of the country. When? During winter. So our winter, remember, it would be influenced by the position of the 3 high pressure cells. So the position of the Kalahari high pressure cell would bring in clear skies, dry conditions. When? During winter. This is because it is dominating in the lower levels of the atmosphere. So what dominates in winter would be this Kalahari high pressure cell. And remember, its characteristic, we said it's subsiding air. So if the air is subsiding around a high pressure cell, we cannot then expect the formation of clouds and any form of rainfall. Hence, we say that it brings in the dry conditions over the interior. So there is subsidence of air, and the air that subsides, it's hot and dry, and then it doesn't lead to the development of the clouds then. Okay, then we look at the influence of the South Atlantic high pressure cell, which we find on the west coast of the country. The circulation around the anticyclones, it's anti-clockwise. So the air moves there in an anti-clockwise. That is due to the rotation of the Earth. So the anti-clockwise movement of air would then bring cold air that is picked up from the Indian Ocean. So there's cold currents that are blowing into the west of the country. So then it would bring in that cold and dry conditions over the west coast of the country there. And then the influence of these South Atlantic Ocean is that it brings in the southwesterly winds. So you can even see from the direction that is shown here that the winds that would approach on the west coast of South Africa would be coming in a southwesterly direction, blowing towards the land. And then therefore, it is responsible for dry conditions along the west coast. The cold and dry air that comes in here, obviously, as I've indicated, it is dry, so it doesn't carry any moisture. So there's little of cloud formation that it would be formed, and except that it can result in the development of advection fog over them, the west coast then. So because of its cold and dry conditions, it would then bring in dry conditions over the west of the country. And then let's look at the influence of the South Indian. The South Indian, in that anti-clockwise movement that I have referred to, we see the air that is picked up there. It would be warm, and it then brings in the warm and moist conditions over the east coast of the country. And then we then have northwesterly winds. So the winds that are blowing in that direction would be your northwesterly winds. And then because now it is over the warm ocean, it would bring in rain over the eastern parts of the country, which explains why the KZN and certain parts of the east coast are experiencing high rainfall percentages. It's because of the influence of the warm Mozambique current, which brings in humid and moist conditions over the east coast there. All right, we are now going to look at the general characteristic of all three high pressure cells. So what we have here is the cross section of the country of South Africa, where now we're indicating South Africa, and this is your east coast over the Indian Ocean, and then we've got the west coast that has the Atlantic Ocean. And then what we can also identify there are the escarpments over the west of the country, the escarpments that we can identify there, and also onto the east of the country there. So all these areas are your coastal plain. So these are all the areas that form part of the coastal plain along the Atlantic Ocean, and these are all the coastal plains that we find and identify along the east of the country. And then in the interior of the country, what we can identify them is, before that, we can identify the over the west, what cell can we find there, and also looking at the east, which cell can we identify there. So over the west, we said we can find the South Atlantic high pressure cell. So You shouldn't confuse the two. I said your guideline is the ocean over which these high pressure belts are formed. And then on to the east of the country, we have, rather before the east, we're looking at the interior. In the interior, we've got the Kalahari high pressure cell. So from the map that you were looking at, we are now looking at the cross section of the very same map that you were looking at in this slide before. So now here we can identify the Kalahari high pressure cell, which we find in the interior of the country. And over the east coast, we can identify the South Indian high pressure cell there. So this is the location of the 3 high pressure cells as you see it on the map, and here now indicated on the cross section. Okay, so the influence of the 3 high pressure cells would still be as explained in terms of this. It would bring in the cold and dry air conditions over the west coast of the country because of this anti-clockwise circulation. And here we are looking at the South Indian high pressure cell, which also indicates that anti-clockwise direction, which would bring in the moist, warm conditions over the east coast. Okay, so the inland, we said it is influenced by what? Mainly by the Kalahari high pressure cell. And then this Kalahari high pressure cell, its position would be determined by whether it is summer or winter. And we are also going to look at how then the position of the Kalahari high pressure cell would influence the weather conditions over the interior of the country, as the Kalahari high pressure cell would shift north in the summer, and then it would shift south in the winter. So its concentration over winter in the interior of the country would impact on the weather that we can find in the interior of the country during winter. And when it shifts in the south, in the northerly direction, it would also have an impact on the weather condition that we can find in the summer in summer then. Okay, so boys and girls, there is a worksheet that we are going to give you an opportunity to look at, and you are going to be given 2 minutes to work on this worksheet, which then says, as I'm showing you the questions here, you should either take a screenshot of the questions, and then you then have to work out your answer, right? Let me just go through the questions. The subsiding air causes semi-arid conditions on the west coast of South Africa. Number 2, in summer, this pressure cell is found at a higher altitude due to surface heating. Question 3, the subsiding air forms an inversion layer in winter that prevents moist air from reaching the interior. 4, the ridging of this pressure cell results in rainfall over the southwestern Cape. 5, interaction with coastal low results in bergwind conditions. Sometimes, that's for question 6 rather, sometimes this pressure cell is known as a blocking high when it is in the path of a mid-latitude cyclone. And then the 7th question, this pressure cell is generally associated with fog and reduced visibility. Okay, boys and girls, I am going to give you 2 minutes to quickly jot down your answers, and then I will then show you the answers that would be deemed correct in these questions. Your 2 minutes starts now. Okay, boys and girls, you have your questions. Then let's look at what would be your answers for these questions. I am just going to move on to the slide that has got your answers. I hope you have your questions that will help you to see why those answers are correct. Then the first answer would be your South Atlantic anticyclone. You read the statement on your site, and then you look at the answer there. And then if you need clarity, you can also refer the question back to your teacher, and then the teacher will be able to help you understand it. Right, the next answer is Kalahari anticyclone. Then for number 3, your correct answer is Kalahari anticyclone. And then number 4, the correct answer is South Atlantic anticyclone. Number 5, Kalahari is the correct answer. Number 6, South Atlantic anticyclone. Number 7 is South Atlantic anticyclone. As I have indicated that for me to go back, it would take much of our time for us to be able to complete the presentation. But these are your answers, and then you can refer the explanation to your teacher. Otherwise, I would have the questions so that I can be able to answer, to explain there. Right, so now we are looking at the subtropical anticyclones, how the anticyclones influence South Africa's weather and climate. Remember, we said these are the 3 high pressure cells that are very much important in terms of determining our weather and climate in South Africa because of its position over South Africa. Right, okay, we've got a diagram that is showing you the cross profile of South Africa on the east coast. So what you can identify is the escarpment that I have referred to, and then also we can identify the Indian Ocean there. Part of the plateau, it is shown there. So we don't have the other the west coast of the plateau indicated there. Right. Then we are looking at which conditions. The summer condition. We are looking at the influence of the high pressure cell when in summer. Okay. So during the summer season, we've got more of warm air that rises over the interior of the country. That is because of the thermal low pressure that develops in the interior of the country. So there's more of convections, which results in warm air rising from the interior of the country. So when warm air rises, then we see the development of what? Of an inversion layer above the escarpment. So more convections of air results in the position of the development of the inversion layer being way above. So this is key in the statement. The inversion layer is formed above the escarpment. So the higher you go, the warmer it is there. Right. So how then is the position of the inversion layer having influence onto South Africa's weather? We can see, and mainly, remember I said it's because of the movement of the Kalahari high pressure. So if it's summer, the position of the Kalahari high pressure, it's more in the northerly direction. It has shifted in the northerly direction, which then says even the high pressures, they follow the direction of the ITCZ, which then says the Kalahari high pressure would be in the north, and the 2 other high pressure cells that we have discussed here would also move closer now to the country if it is winter. But in this case, we are looking at the influence of the Kalahari high pressure, which has moved in the northerly direction. So the movement of the Kalahari high pressure cell in the northerly direction would mean that when air descends around the Kalahari high pressure, the inversion layer would not be formed in the lower levels of the atmosphere, but rather it would be formed at the higher levels of the atmosphere, which then becomes an inversion layer above the escarpment. And how then does this influence the weather over South Africa? So those arrows are just showing you the descending air around the Kalahari pressure that is further in the northern, further north, not in the northern hemisphere rather, but just in the northern direction. And then the warm air is the one that I have indicated to you, that we've got more of warm air that is rising from the surface, and then there's more convection currents, which has resulted in the development of the inversion layer there. So the position of the inversion layer will then have an influence over what? Over the South Atlantic high pressure cell, which we have on the east of the country, and more of warm air would be able to move in that direction. So we've got that anticyclonic movement of air, and then we've got more of warm air that is able to pass through and reach the interior of the country. So as air is moving in an anti-clockwise direction, the warm air from the Indian Ocean would be able to reach the interior of the country. So if warm air is able to reach the interior of the country, it will bring in the warm and moist air conditions, which would then be associated with what? With rain, heavy rainfall or thunderstorm, or just rain in general. So the conditions over the interior of the country would then say that then in summer, that's why the interior of the country experiences rainfall. It is because of the warm, moist air that is able to pass through and get onto the interior of the country. And there is nothing that is on its way. So it is able to reach the interior, and then we are going to have the development of weather elements such as line thunderstorm. So the line thunderstorm would mean that alongside the east of the country, we will have more of convections, and there would be more cloud development along that east coast of the country, or the eastern part of the country rather, not the coast, the eastern part of the country. And we have the development of large clouds, and the line thunderstorm would then be found onto the eastern part of the country. All right, and then here now we're looking at the influence of the anticyclones on South Africa's weather and climate, when now we are looking at the winter. So over winter, we then look at the influence of the South Atlantic high pressure cell, which is also influenced by the position of the Kalahari high pressure cell. I have indicated to you that, okay, in winter, the Kalahari high pressure cell would move to the southerly direction. So the interior of the country is experiencing cold temperatures. It is winter. So when the Kalahari high pressure cell is now moved to the lower levels of the high pressure cell, the inversion layer will now be formed below the plateau. So we can see that now the inversion layer, it's no more high up in the plateau, but then now it's lowered. So this inversion layer will now be lowered due to the position of the Kalahari high pressure cell there. So how then will this influence our weather? We have the descending air over the Kalahari high pressure cell. So the air that descends results in the inversion layer being formed below the escarpment. So air descends around the Kalahari high pressure, and then the inversion layer is formed there. And then over the Indian Ocean, what would happen then is that the warm, moist air that is supposed to be reaching the interior of the country will not be able to pass through. Why? Because the inversion layer would stand in and block the warm air from reaching the interior, which explains then why the interior of the country in winter there's no rain, as there is less of the warm moist air that is able to pass through. So the warm air will just be circulated over the Indian Ocean, and that's where we can only find rain being formed, but the interior would be dry then. So warm moist air is blocked then, and then the interior would be cloudless and it will have dry conditions. Right, boys and girls, there is another worksheet that you can also have 2 minutes to work on it. The questions are: figure 2.1 shows anticyclones over South Africa. Match the anticyclones with the description given below. Write only the answer next to the question number in the answer book. Example 218, Kalahari High. So these are the statements or the descriptions rather, that you need to match with with any of the anticyclones that we have discussed. Okay, the pressure cell that results in high rainfall along the coast of South Africa. Okay, the pressure cell that pushes cool air into South Africa from southwest. A weak cell that allows rising convection currents to reach the interior in summer. So you must underline your keywords before you come up with your answers there. The anticyclone that causes clear, stable conditions over the interior of South Africa in winter. Then the 6th question, the anticyclone that shows the smallest seasonal locational changes. The last question, the pressure cell that is responsible for the vertical position of the inversion layer during summer and winter. Right, you have 2 minutes to complete this worksheet. My colleague Hendrina will continue with the answers onto this worksheet in the next 2 minutes.
the reason for that southeasterly winds blowing over the southwestern Cape is because the South Atlantic high pressure cell reached in south of the country. Take note there, it's during the time of autumn. It's really autumn. Now, the high pressure now, if you can see, is reaching in south of the country. So this mid-latitude cyclone cannot move. That is telling us it's still summer conditions. This high pressure cell is blocking off the mid-latitude cyclone. So this mid-latitude cyclone will not be able to move over the country because the South Indian Atlantic high pressure cell is reaching in south of the country. High pressure cells are located far south, therefore mid-high pressure cell, you can see it is lying a bit north. It has moved north. That is because of the ITCZ that has moved north. Now I can see my mid-latitude cyclones now can move over South Africa. And I know it is winter conditions. Can I just take a sip of water? I want you now to look at the following video.
Please, people, take note about this, that you can apply this to line thunderstorms and the South African bergwind. Okay, very quickly, let's have a look at the factors that influence the climate of South Africa. Right. Firstly, we must know the influence of the oceans. Now, Matrix, this you've learned from primary school level already. When you started working with atlases, there you learn that we've got the warm Mozambique and the cold Benguela. Right, so here we've got the warm Mozambique, here we've got the cold Benguela, and here as we just touch here on Eastern Cape and start to move towards Western Cape, it is called the warm Agulhas. So these are your what you must understand actually is that you've got warm water here on the eastern side of South Africa and cold water here on the western side of South Africa, and these two have a huge influence on the climate of South Africa. Hang on with that, we'll see what happens later on. The second thing that you must know, warm and wet climate, and on this side, because you've got a warm water here, it will be warm and wet here, and on this side, it will be cold and dry. Now, okay, the second thing that you must know is your subtropical anticyclone. You must know where they are, you must know where they are located, and you must know the names. There are three of them influencing the climate of South Africa. The South Atlantic high pressure, the South Indian high pressure, and the Kalahari high pressure. The Kalahari high pressure is found in the interior, and obviously these two will be found in the oceans. Now, Matrix, you've got to take note about what I'm going to say now. Remember, there's no such thing as the Atlantic high pressure and the Indian high pressure. You are not going to get your mark, right? If they ask you to identify the high pressure at 1 or A or whatever, and it's in the Atlantic Ocean, the name is the South Atlantic high pressure. Please don't make a mistake and only say Atlantic high pressure. You're going to lose unnecessary marks. The same with regard to the South Indian high pressure, not the Indian high pressure, the South Indian high pressure. Please don't forget that. Okay, so let's have a look at this. So here we've got the Kalahari high pressure, and here we've got the South Atlantic and the South Indian high pressure. As we progress, you will see that the South Atlantic and the South Indian high pressure, they play a very, very important role when it comes to line thunderstorms, and your Kalahari high pressure plays a very important role when it comes to the SA bergwind or bergwind competition. So you must know the role of each of this. We'll have a look at this within the next few minutes. Okay, and the last thing that you must know with regard to the climate factors is the plateau or the interior, which is very high, and because it's high, the higher you go, of course, the colder it will get. Now, Matrix, if you have a look at these factors, now, okay, you must know these factors, but what's much more important is the application of these factors. You must be able to apply these factors. You must know how these stuff work. And And if you know how these things work, it's going to be very easy for you to explain the Bergwind conditions, and it's going to be very easy for you to explain line thunderstorms.
Thank you, boys and girls. Now we go to the South Atlantic anticyclone, which is located at the Namibian coast. It's a semi-permanent and semi-stationary high-pressure cell. He just move a bit north or south depending on the season. The changes are seasonal and it's linked to the seasonal shift of the ITCZ. This anticyclone is normally associated with clear, stable weather. Remember, it's a high-pressure cell, so air moves anti-clockwise around the system. The cool, dry air latitude cyclones away, as we have seen previously. Move from the coast in summer. So, there is my South Atlantic. What is magnetic declination and magnetic bearing? Magnetic declination is the angle between true north and magnetic north. The magnetic declination changes yearly and must be calculated. The magnetic declination can change in two directions. It can either move west, where magnetic declination will increase, or it might move east, where the magnetic declination will decrease. True north, there's my magnetic north. Magnetic north changes every year due to the change in the magnetic fields of the earth. So, is the month and year when the mean magnetic declination was recorded. Therefore, in December 2013, the mean magnetic declination was 17 degrees 54 minutes. So in December 2013, the difference between the true north and the magnetic north was 17 degrees 54 minutes. That was December 2013. It's very obvious that in 2024 it will not be the same. Therefore, we need to calculate what it is today. 2013 refers to the years that were used to calculate the mean magnetic declinations. We don't use those dates when we determine magnetic declination. The mean annual change refers to how the magnetic declination each year changes. Now, how to determine it? Use the information on the map and determine the magnetic declination for 2024. That's how the question will read. So, I go now to step 1. What is step 1? I have to calculate the difference in years. Difference in maths means I must subtract. So, I take the current year, in our case it's 2024, and I minus the year on the map. So if you have that in 2024, I minus that 2013. Where do I get that 2013 from? I get it from there. So if I minus the 2, I will get 11 years. So first of all, you subtract the 2 years. Step 2, state the mean annual change. Now that's your information. That is the mean annual change. This step is given to you. So the mean annual change is 5 minutes west. So now I need to calculate the total change. That means the difference in years that I've calculated, and I need to times it by the annual change. So there's my total years. Remember, it's 11 years. And each year it moved with 5 minutes, so I say 11 times 5 minutes. So that means the total change will be 55 minutes. step number 4. Add the total change, which was that 55 minutes, to the magnetic declination for 2013. So in 2013, the magnetic declination was 17 degrees, 55 minutes, as we saw there. The total change is the 55 minutes west that we have calculated previously. So if I add up the two together, I must remember, always add minutes of minutes and degrees with degrees. Now, if you have your calculator, you do the following. You type in 17, you click on that symbol on your calculator, then you put in 54. After that, you click on that one again on your calculator, then 55, then that one again. Then add minutes to minutes and degrees to degrees. So if I have 54 minutes plus 54 minutes is 108 minutes. Now above 6, that 108 is above 60 minutes. So I have now, what you need to remember is that 1 degree equals 60 minutes. That means I'm going to take that 108 that I have there, I'm subtracting 1 minute, which is 1 degree, and I will get 48 minutes. Therefore, 108 degrees minutes equals 1 degree, 48 minutes. Now, my calculation will be 17 degrees plus 1 degree is 18 degrees, 54 minutes plus 48 minutes. Oh, give me 102. Now I must remember, 102 is 1 degree, 42 minutes. So I add that 1 degree to that 18. So I will have 19 degrees, 42 minutes is the answer for that question. Remember, the direction must be indicated. Those words west of true north needs to be there. Now for magnetic bearing, we need to use the following formula. Magnetic bearing equals true bearing plus magnetic declination. So I determined the bearing between the 2 points. For that, I put down my protractor. I first combine the 2 places, put down my protractor, I read clockwise, and I get the answer is more or less 110 degrees. Now you use the information on the map and you determine the magnetic declination. Remember, we have done that now. So we take that true bearing, which is 110. We calculated the declination. So we take that 19 degrees 42. I say degrees add to degrees gives me 129 degrees. 0 minutes plus 42 minutes gives me 42 minutes. So the answer now, the magnetic bearing between the 2 points is 129 degrees, 42 minutes. Let's look at the following video.
Let's move on and have a look at the following question, which has to do with magnetic bearing. Now, magnetic bearing is actually very, very easy, because if you have a look at the word magnetic bearing, in other words, the first thing you see, it has to do with your magnetic declination, as well as the simple thing regarding that you can calculate magnetic bearing, because actually the two must just be added. So let's have a look at magnetic bearing. Here we've got a question regarding magnetic bearing. Calculate the magnetic bearing from spot height 97 to trig station 94. Here's spot height 97, here is trig station 94. So we must calculate the magnetic bearing from here to here. Now, this question comes from last year's question paper. So you can see how an important calculation this is as well. Okay, so the first thing that you must remember is, what is magnetic bearing? Magnetic bearing is your geographic bearing plus magnetic declination. Now this becomes very easy, because if all the schools, 4 of you, could do magnetic bearing, magnetic declination, then it means you can calculate magnetic bearing, because all you must do is to calculate your declination, add your bearing, and that's your answer. So let's have a look at this. Our question, let's have a look at the question again. Calculate the magnetic bearing from spot height 97, which is here, to our trig station 94 there. So let's just do that. Now, if you have a look at this, then your bearing would be 192 degrees. Now, you need your protractor to measure this. Remember that north must always show north. And then you will measure the angle from here right around this way, and you will get 1. So now I have my bearing. I've got my geographic bearing, which is 192 degrees. Okay, so that's the first part of the calculation. So now let's have a look at the second part of the calculation. It is easy because we've just done magnetic declination. So let's have a look at this. In this case, the magnetic declination was the following. The mean magnetic declination was 25 degrees 29 minutes west of true north in 2001. Mean annual change was 9 minutes towards the west. Okay, so now let's have a look at that. Now, the question was that you had to calculate it for 2010. Please bear in mind that this question was in last year's question paper. So let's have a look at this. So we must calculate the magnetic declination for 2010. Now that's quite easy, because this means that the difference in years, it's 2001 and 2010, the difference in years would be 9. So what must I do? That easy step, take the 9 times 9, and I have a difference of, and I will see it would be 81 degrees towards the west. Towards the west. So what's happening now is that we've got to add the 25 degrees and 29 minutes west plus the 81 minutes towards the west, and my answer there would be 26 degrees 50 minutes west. Now people, remember that are 6 degrees 50 minutes towards the west, and my answer there would be 218 degrees and 50 minutes towards the west. So people, just remember, when you do the magnetic bearing, please people, remember, it's simple. But the only problem is you must know how to calculate your magnetic declination, and then a very, very easy sum that you've got to work out. You've just got to add the geographic bearing to that, and you've got the answer. So this is quite an easy one, only if you know how to calculate magnetic declination. People, if you are still unsure about calculate your bearing, please go back to your teacher, ask him or her to show you how to calculate the bearing of anything on your topographic map, in order for you to also do your magnetic bearing successfully.
Thank you, boys and girls. Just to show you that whatever we say, other people is confirming that. Now we come to map scales. We have 3 types of scale: a representative scale or a ratio scale, a line scale, and a word scale. A representative or a fractional scale is also called a ratio scale. It's a numerical way of showing how greatly ground distance have been reduced. It's also referred to as a numerical scale. And it can be one of 2 ways. It either can be 1 over 50,000, or as a ratio where it is 1 to 50,000. On a topographic map, it will look like this. And then on the orthophoto map, your scale will be 1 to 10,000. That's a ratio scale. The line scale appears at the bottom of the map. It looks like this. It's a horizontal line drawn on the map, which is divided into a number of equal parts. A line scale is accurate and no calculations are used. And the line scale is then divided into two parts. To the right of 0, here 0, to the right. Each division is a distance of 1 kilometer. So there is 1 kilometer, 2 kilometers, 3 kilometers, etc. Here you can see it's also written there. Then to the left of the 0, it's the distances represent 1,000 millimeters or 1 kilometer. This is subdivided into 10 equal parts. So here's 100 meters, 200 meters, 300, 4, 5, 6, 700, 800, 900 and 1,000. So from there to there it's meters, from there to there it's going to be kilometers. The word scale indicates scale by means of a word scale indicates scale by means of a verbal statement, such as 1 centimeter on the map represents 500 meters on the ground. The scale is given in words. Note that the statement mentioned two distances. The smaller distance refers to the map and the larger distance refers to the ground. That centimeter, I'm working on a map in centimeters, and in reality I'm working with meters. Now if I look at this, I will have a large scale and a small scale. A large scale map covers a small area and shows a lot of detail. For example, your orthophoto map. It's 1 to 10,000 is a large scale map, as it covers a small area and shows a lot of detail, where a small scale map covers a large area and do not show much detail. For example, a 1 to 50,000 topographic map. So know the difference between a small scale and a large scale map. Listen to this video.
Today I'm going to focus more on the ratio scale. For me, the ratio scale is a better way to explain how a map, not how a map, but how a certain area was made smaller in order to fit it onto a piece of paper as you can see there in the top right hand corner of the map, that's where you will find the ratio scale. That is what it looks like, 1 to 50,000. And then if we move to the bottom of the map, you'll see that there's also a line scale or a linear scale. That is what we spoke about in one of the previous lessons. There it is. It says 0, 1, 2, 3, 4, and 5 kilometers. And as I explained in the other video, and if you haven't seen it, then please go and watch it in order to understand what it's all about. But like I said, we are not going to focus on this today. We'll be focusing on the ratio scale that we see here in the top right hand corner, 1 to 50,000. Right, so here's my ratio scale, 1 to 50,000. Now, what it basically says is that 1 centimeter on your map represents 50,000 centimeters in reality. In other words, if you take your ruler and you measure exactly 1 centimeter on your map, then if you go to that specific place in real life, then you will find that it's equal to, or that it is 50,000 centimeters. Okay, so let's make it really, really simple. Many of the kids in my class might ask me, sir, but we still don't understand. And I love it because it's an honest question. So let's have a look quickly. Let's break it up. Let's make it really, really simple. Let's say we have Johnny. Here's Johnny. Johnny needs to eat a bit more. But anyway, so Johnny is in my class. And we get an artist to come and make a nice statue of Johnny. Okay, let's just write his name here, Johnny. And we get an artist and we say to this artist, listen, we want a statue of Johnny. He's been the geek of the week. He doesn't know whether he's excited about it or not. So Johnny keeps a straight face, and this artist comes in and he makes a statue exactly the same size. Now if we take a ruler and we measure 1 centimeter on the statue's arm, then we will find that it will be exactly the same distance on Johnny's arm. In other words, 1 centimeter on the statue will represent 1 centimeter on Johnny. Now, so the scale for the statue would then be 1 to 1. Because 1 centimeter on this arm represents 1 centimeter on Johnny's arm. Right. Now, Johnny isn't happy about all of this because he wants to take his statue home. He doesn't want to leave the statue at school. He wants to go and show his parents, Mom, Dad, look, I was the geek of the week. He wants this statue to be 10 times smaller than him. So it's 1/10 of his size. Now, once again, I'm going to do a rough estimate here. Let's say this is 10 times smaller. And now if we take a ruler and we measure 1 centimeter here, then it will represent 10 centimeters on Johnny's arm. So now the scale would be 1 centimeter, because 1 centimeter represents 10 centimeters in reality. No questions. That is the beauty of teaching on a video. Nobody asks me any questions, but you can rewind this video as much as you like and eventually you will understand it, or let's hope so. And now we can write it as a fraction scale once again, and it will give you 1/10. So let's wrap it up. A statue is a representation of Johnny. Now, the best representation of Johnny would maybe be to make the representation of him exactly the same size as Johnny. But it's not the best way, because he wants to take this representation of himself, he wants to take that thing home, and he wants to be able to carry it around with him. And so in order to make this representation or the statue a more practical thing to carry around, we had to make it smaller. In the same way, a map had to be made, or not the map, but a certain area or a representation of a certain area had to be made a lot smaller in order to make it more practical, so that you can fit it onto a piece of paper and then eventually use it in a classroom or wherever you are traveling, whatever the case may be. Thanks once again for tuning in. In the next lesson, I'll explain how to use this ratio scale in order to calculate distance.
Thank you, boys and girls. Let's go on. Now we come to worksheet 3. Here we give you this diagram on anticyclones over South Africa, and here I am giving you the question. Name the high pressure cell B. Why does high pressure cell B dominate the interior of South Africa in winter? Give a reason for the lack of rainfall associated with high pressure cell A. Explains the change in position of the anticyclones over South Africa between summer and winter. And 5. Explain why the South Indian high pressure cell feeds more moisture air over the interior in South Africa. Please take note of the verbs in the question. Name means you need to state something, give, identify or mention. Explain means you must make clear, interpret and spell out the material you present. And then another question is explain why. With explain why, you must make clear, interpret and spell it, but you have to elaborate on the question as it says why. Due to time, I'm going to go over to the answers immediately. I would prefer that you stop here, do the answers your own, and then after that you check your answers with my answers here. Question 1's answer is name the high pressure cell at B. There's B. It will be the Kalahari high pressure cell, continental high pressure cell. Why does high pressure cell B dominate the interior of South Africa in winter? Because in winter we have lower temperatures causing air to subside or to sink, and it creates a high pressure. Or there's less heating of land surface which will decrease convection. Any one of those two. Give a reason for the lack of rainfall associated with high pressure cell A. Subsiding or descending air heats up and does not allow for condensation to take place. Subsiding or descending air does not release moisture, and it's located over a cold ocean. Explain the change in the position of the anticyclones over South Africa between summer and winter. In summer they occupy a southerly position because the sun is over the Tropic of Capricorn, and all pressure systems move south with the apparent movement of the sun. Or in summer, due to the intense heating of the land, the high pressure system moves further out to the sea. In winter they occupy more northerly position as the sun is overhead of the Tropic of Cancer, and all pressure systems move north with the apparent movement of the sun. In winter they are close to the land because the land is cold. Any two answers here. And then the last question, explain why the South Indian high pressure cell feeds more moisture over the interior in summer than in winter. The inversion layer is above the escarpment and allows the moisture to feed over the interior. It allows warm moisture air to rise and condense on the windward side of the escarpment. And intense low pressure over the land in summer leads to the convergence of air. Moisture air from the South Indian high feeds into this low pressure over the land. Increased evaporation due to higher temperatures over the Indian in summer, and this feeds moisture into the land. Or the South Indian high is away from the coastline and the onshore winds have a greater distance to travel in more moisture over the land. Any three of this. With this, boys and girls, we thank you for logging in and good luck.